Hello, everybody. My name is John Bandela, and thank you all for coming this afternoon. I'm going to talk about channels as an alternative to callbacks and futures. I was originally scheduled to give this talk on Monday, but unfortunately, my flight got canceled at Sunday night flight, and after spending more time, I think, at the airport than in the air, finally arrived here. But looking back on it, it could have been worse. I could have been traveling with Tom Hanks. Just a little bit of background about me. In the picture, the guy that you can't really see the face, that was me. Just a little bit. What we were doing there is we were doing a awake craniotomy, which is basically you put the person to sleep, open them up, and then once the skull is off and the brain is exposed, you wake them up. And then you can test different areas of the brain. So they had some people with cards, the neuropsychology people. They're asking for naming tasks and stuff, and then we would zap certain areas of the brain. And if he all of a sudden stopped in the middle of one of his words, we'd know, hey, you don't want to take that part of the brain out. After a while of doing this, I decided I wanted to do something with a little bit less scary undefined behavior. So C++ it is. Nasal demons are preferable to nasal brain fluid.
So were you doing this for a reason or just fun?
No, for this particular operation, this person was having seizures that could not be controlled by medication, and the seizures were coming from the speech area of the brain, so you had to know which parts of the brain you could actually take out and not to stop the seizures. All right. So today, our main focus is going to be on asynchronous programming. Is everybody here familiar with asynchronous programming? Raise your hands. Okay, good. So asynchronous programming, instead of asking, hey, are you there yet? Are you there yet? Are you there yet? You just leave a note saying, call me, and then, at the correct time, you get called. So C++ knows about two main models. The first is callbacks, and the other one is futures that are in the standard. So callbacks is the oldest model. When something needs to happen, it calls a user-supplied function. The synchronous example is qsort for the comparison, and an asynchronous example, even from C, is like signal. It happens asynchronously. More recently, with ASIO and the upcoming C++ networking TS, we have async receive buffer, where async receive, where you supply a buffer and a callback, and when you get that data, you receive the callback. Futures. So futures are, this is the excerpt from Anthony Williams' C++ Concurrency in Action. Basically, it's a model for a one-off event that you can start something up asynchronously and have it let you know when it's done. So there's the problems that in the future, we've got two types. The main stuff that's in the standard now is the blocking type. You have a future string, and you read from a file, call f.get for blocking, and it blocks until then, and then you use it. Early on, it was identified that, hey, maybe blocking on future.get is not such a great idea. So now we have the Concurrency TS that was published in January of 2016. That has future.then, future.whenany, and future.all. So here's an example of future.then, where instead of, in the previous example, we were blocking. Instead, you supply a .then, and it'll let you know when the future is complete. And in addition, we also have whenany. So if we want two futures, and we want to say, hey, when this happens or that happens, let me know when either one happens. We can also do that via the whenany. So callback versus future. So callbacks are conceptually simple. They're efficient. But the downside is they're difficult to compose. Think about how you do whenany with just using callbacks. You'd have to figure that out every single time you did that. Future, on the other hand, it is more complicated. Because of that, it can be less efficient. But the advantage is it's easy to compose, for example, using whenany. Unfortunately, the concurrency TSs are not widely implemented yet. So for a lot of these places where we use futures, the closest I could find this in general use is the Boost futures. So that's what I'll be using in my examples. So why do we need anything else besides futures and callbacks? So futures are basically designed for one-off events. However, there are many situations that don't produce one-off events, but that produce a stream of related events. And we want a way to deal with the stream of asynchronous events efficiently while still being able to compose them. And we can call a stream of asynchronous events for this purposes a channel. And just as an exercise, we'll talk about this later. I mean, think about just using futures. How would you design something like this, where you took an input that was serial, for example, you read from something, and you did like a fan out to process stuff in parallel, and then put it all back to output serial. We'll get back with this. Keep this in the back of your mind. So we're going to talk a little bit about performance. And like I said, these are for ballpark numbers for doing this on my machine. And with that caveat, let's look at some stuff. So first of all, let's look at callbacks. So we're going to use the Boost executor loop executor. So basically, that's an executor that you can have control over when it executes. And we're just going to submit a bunch of callbacks to it and run the queued closures. Okay? And then this is future. So it's a little bit hard to use future in a loop, but this is close enough proxy. So we have a promise. We get the future from the promise. And then we set a future that sets a done value equal to true. We set the value for the promise. And then we run the queued closures. Which do you think is faster? This one or this one? And how much faster is callbacks, you think? So it's about, in my machine, it was like a factor of like around 6. All right, so hey, maybe just dealing with futures is, doing that kind of asynchronous stuff is just inherently hard to do and inefficient. Well, let's take a look. Anybody know what this is? Yeah, that's the Go Gopher, all right? So let's just do a simple thing. So we have a writer, and so this is not a Go conference, so I just basically kind of learned enough Go to be dangerous for this, but basically the declarations, the function arguments are kind of like backwards in terms of that. So C is actually a channel of integers, count is an integer, and then up until we reach the count, we just write to the channel. And then we close it. And then for the reader, we read from the channel, and so basically it returns the equivalent of like a pair. One is the value which we're ignoring, and the other one is OK, which returns false if the channel is closed. So we return, and then we signal the outside thing saying, hey, we're done. And we do a timing of it, and here's what it looks like. So it's pretty close to callback and way better than future. So this is actually kind of embarrassing because this is what we have, and we're stuck there. Thankfully, we've got Boost. So anybody know what came out in Boost 1.62, the beta? Go ahead. Boost Fiber, yes. In fact, that was such a big deal, my local grocery store was talking about it. So anyway, now with Fiber, so let's see what we can do with it. So we're going to do the same thing. So you notice our code looks a lot cleaner already. And so basically, one to count, we push to the channel, and then we close. And then we read from the channel, and then if we get a status that it was, we pop from the channel. If we get a channel the status was closed, we return. And this is what it looks like. So it's quite a bit better than future, but not as good as Go or the callback. So in addition, the other thing that we lack that it doesn't have is it doesn't have anything equivalent to select, which is like the equivalent of when any for future, when any for like channels. So we can't say, can you read from this channel or that channel? and do that. And it only works with fibers. So we're gonna in this session, we're gonna write something and design something that will help remedy that situation. So I'm a big believer in TDD. And I think that if you don't do TDD, you'll never be a good developer. Agree? So thought-driven development. So just to warm us up, can anybody figure out what C++ feature this is? What is it? No? Okay, let me arrange these in order. What is it? Who said that?
Generic lambdas.
All right, why? Yeah, Gene, Eric, Lambda. Okay. All righty. All right, so our goals is, so let's write a C++ channel that's going to have 0 dynamic memory allocations once channels are set up, other than required for moving. We want to have channel select, and we want it to be ergonomic, and we want it to be adaptable for use with other types of coroutines. So just a note on adaptability. So these channels that are developed in this thing, I've got on my GitHub. They support actually the coroutine TS, like co-wait. I've tested it, I think, in the implementation that's out in Visual C++ 2015. And I also wrote a library of stackless coroutines that's a header-only, macro-free implementation of stackless coroutines. And this was originally written as a demo for that library, and then this kind of grew up out of it. So as mentioned before, we're going to be using the coroutine TS. So how is a future implemented? There's several ways to do it, but most of the ones that do here, basically you have a future and a promise, and you have a shared state that's dynamically allocated. There's been several talks about ways to make more efficient futures. I know back in 2013, I think Tony Van Erd gave a talk on a non-allocating future. But the ones that are out there, the ones that are implemented, use some sort of shared memory thing. So every time you create a future, you're making an allocation. So somebody comes to me and says, hey, it hurts when I do this. The answer is, don't do that, right? So this is so here's an example here. So this is from Gore's talk before on coroutines. But this is a very trivial, trivial thing that basically makes a connection and reads from the connection. If you use future.then, it looks like this. And then we have coroutines to the rescue, which makes it again looks like this. But I think the underlying problem with future is, take a look at the connection.read. So with future, we're reading that in a loop and we're creating futures. The connection.read pretends that just about everybody in the world will call it, right? However, you're probably calling it in a loop, and it's probably going to be one thing that's calling it. It's kind of like the difference between checking into a hotel every night and actually renting a place for a year. Like, you can establish an ongoing long-term relationship, and you can decrease transaction costs. So just a little bit about how coroutines work. So go to Gore's talks. If you haven't gone, if you missed them, watch them online. But basically, coroutines simply are a place to store variables across coroutine invocations and the ability to suspend and resume. So place to store variables. So basically, we store the parameters and the locals and the temporaries. And the middle stuff is actually how Go looks. And the stackless coroutines are on the right, where it's actually not part of the program stack, so you can have basically billions of these. And then we want the ability to suspend and resume. So we're going to talk with the first goal. How do we write a channel with 0 dynamic memory allocations once channels are set up other than required by moving? Any ideas? All right, so we'll do this. So here's the idea. So we have a reader coroutine and a writer coroutine. And what we do is we actually store a node for an intrusive linked list as inside the coroutine function. And then we have a channel. The channel is allocated. Like I said, once everything's set up, that's when we don't do any more allocations. And then we write it into an intrusive linked list of readers or writers. And then once we match up a reader and a writer, we do a move across the values. And because the coroutines, as long as, as soon as we write into that, we suspend the coroutine, we know the values are going to be there until we need them. So show me the code. So this is we're going to start with a node base. So basically this looks, like pretty much, bog standard linked list node. We have a next and a previous, and then we're going to store we're going to store a function pointer and then like a void pointer to some data that we can use that the function pointer can use. And then we'll pass this node base to the function pointer. And then we just store a flag for closed. All right. And then we have a node T that just derives from that and just includes like the value that you want. So this is what our channel is going to look like. So we're going to have a node T type, and we're going to have basically two doubly linked lists. One is for read, and one is for write. And then we're just going to have a flag to tell us if we're closed, and then a mutex that we lose, and like an alias for the lock. So we're just going to look for what write does. So when we write to it, we actually take a pointer to a node, and then just, so basically if it's closed, we're going to basically tell the writer it's closed and execute that function. And then we just bail out early. Otherwise, we take a lock, and then we basically detail remove is just your standard linked list remove from the end of the list, or actually from the beginning of the list. It removes the read head from the read list. And then if we don't have a reader, we add that node that we had to the write list. Otherwise, so the else statement means we did find a reader, so we unlock. We move the value from the writer to the reader, and then we close it. We sense that the close is false, so we don't signal it because we closed. And then we call the writer func and the reader func. And then this is the one part I haven't seen other people do. You separate out where the node is stored. So we have a channel writer. And the channel writer actually stores the node. And then this is what the write looks like. So a little bit, how many of you have been to any of the coroutine talks? Oh, good. So a significant amount of you. So basically, when you want to write your own type of coroutine thing, what you want is you want to have some sort of a waiter struct, and then you have three functions that are used that the runtime system will call: await ready, await suspend, and await resume. So await ready tells, hey, are you ready already? And we're never ready. Await suspend, it passes a coroutine handle that we can use to eventually wake us back up. And await resume will, once we woke up, it will call this, and then co-await will return whatever this is. So in this case, we're going to skip await suspend for now. Await resume, we just return true or false whether the node is closed or not. And then we return the awaiter. Any questions so far? All right. So this is what await suspend looks like. So we have from the previous thing, we had the pointer to the this, which is the pointer to the outside channel writer. And then we set the node function. So when we get the node base, we static cast down to what the derived type is. And then we access the data from there. And there's the coroutine handle has a static function that can return us a coroutine handle from a void address. And then we call it to resume. So that's our function. That'll get called whenever we wake up. And then we store the coroutine address in the node.data. And then we write the node to the channel. So this is what our channel writer code looks like. So go routine is basically the promise type. But basically, we take in a channel. The first thing we do is we create a await channel writer, and then we do the count to the right, and then we close it. Same with the reader, So if you look, this code is, there's a lot of people that say, oh, C++ is very low level, hard to use. This code is pretty similar to what you would see with Go. So it's pretty close to the same level of expressiveness in a library form. And so then I ran this code, and what happened? It crashed on me. Any idea why? So if you do stuff a million times, when you do the reader and writer func, you end up growing, you can end up, if you have the right combination of calls, you end up growing your stack as each one keeps on reading and writing, and then you have a stack overflow. So what do we need to fix this? We need to have something in between. Any ideas what we need? We need this guy, the guy in the black mask. He's an executor. And if you look in the background, you see all these ropes. So that's a multi-threaded executor. So the trick is, how do we make an executor without allocating? Our whole thing, okay, well, now if you pass it to the executor, how are we going to do this? Well, what we do is we have the executor that actually uses the nodes as a linked list. So we have the head and the tail as a doubly linked list. And then, like I said, there was no, this is not lock-free. This is just, the most naive implementation you could think of for an executor. So we just, add it, be able to add it, and then a run while it's true, pop one, pull from the beginning of the list, run it, and then, if you don't have anything, wait in a condition variable. So then we rewrite our success. Instead of executing it directly, we add to the executor. Any questions so far about what we've done? All right. So this is what our performance looks like. So if you see, we're actually, can everybody see this? So right there, laser pointer. Let's see. This one is. So right there is where we have the channel with the coroutine, and right here is the callback. So it's about the same speed as the callback. Now, this wasn't the most rigorous of performance testing and everything. So basically, you can see the ballpark. It's in the same range as a callback. So we've actually gotten a lot faster than future, and we're basically in callback territory. But right now, we're not really doing much more than we could with callbacks. So let's move on. Anybody know what this is? So it turns out the Nile is not just a river in Egypt, it's also a river in Sudan. So this is where the black Nile and the blue Nile and the white Nile come together. So we're combining two channels. So our goal was to do a channel select, a when any for channels. So just an example of how you do this in Go with built-in language support. So we have a writer. So what we're going to do is we're going to have two channels now. And for a count, if it's odd, we write to one channel. If it's even, we write to the other. And then we close both. And then for the reader, we do a select. So we don't know which channel we're going to get the value on. So we do a select that comes from a read from one channel or the other, depending on which one is available. So this is basically the equivalent of future when any. So this is how to kind of, just for performance testing, how to do when any in a loop. And it's convoluted. Basically what we're doing is we're using the loop executors, and we're going in a loop. We're doing a selected, as you can see, the selected when any, and then we set up what the selected looks like, and then we set the value to one or the other, and we run the queued closures until we finish. And inside selected.then, we're just careful, because we had to refresh our futures all over again. So if we use one up, we can't reset it. We had to create a new one, put it back in. Anybody have an idea of how this performs compared to our regular future? Any guesses? Elephant, yeah. So it looks like this. So the middle one, you see the middle one? That is future select. Unfortunately, you may not see it. The other iterations are 1,000,000. This one is 10,000 because when I ran it, it get an error saying I'm out of thread resources. I think when any may actually spawn a thread. So this is what it looks like. So yeah, so that's really bad. We're going to leave that out for now. So this was what the Go select looked like. It's about twice as worse as the Go with channels. And like I said, everything is way, way better than future select. So just an aside, when we're designing channels, why can't we just use a stream of futures, right? Just have one where channel is basically a queue that returns a future. I played around with that a couple of years ago. The problem is, what happens to the non-selective future, right? You only want one thing. You did a select. You got 2 futures back. And you did a when any. You got 1. Now the other one becomes available. What do you do with it? Is it lost? Do you drop it? Do you try to push it back in? That's a problem. So we're going to do a little bit of thought-driven development. And here's our idea for how we're going to do select. So inside the node, we're going to have an atomic pointer to a atomic integer that's done. And we separate out what we call the selector. So whenever that triggers, we'll know, that one of these ones in our series was triggered and we won't do it anymore. It'll become more obvious in the code. So let's see here. So this is our node base that we had. And so we just add an atomic int star p done. And then we have some little stuff for handling p done. So basically, we have this thing set done. So if it's null, we return true. And otherwise, so there's 3 states it can be. 0 means we haven't done anything with it. 1 means we've succeeded. -1 means it's indeterminate, keep looping. And we just have a little bit of helper functions where you call set intermediate, which takes it from a 0 to a -1. A clear intermediate success between succeeded, take it from intermediate -1 to 1. Failure, take it from -1 to 0. And set success is from 0 to 1. And we'll see how we'll use this. And then we just have a channel selector that'll hold the atomic variable. So this one we're going to do for reader. So this is what we had before doing anything. So basically, we look if it's closed and the right head is null pointer. We unlock the lock. And before, we just say reader closed equals true, and then add reader and return. So now instead, we say, if it's set successfully, we do it, which means that nobody else has triggered the pdone, or else pdone was null pointer. And if somebody else signaled it, there's nothing we need to do. We can just remove it. We can just ignore it. And otherwise, then we found a matching writer. So before we'd grab the one from the head of the list and use that writer. Now we try to set intermediate on the writer, and that'll fail if somebody else has already triggered that writer. And so the same as before, if we don't find a writer, we add ourselves to the list. This is where we did successfully. And we add this code where we set success on ourselves. That may fail. And if we're able to do it, if we can't do it, then we add ourselves to the list. And we clear we add the writer back because we don't need that writer anymore, and we add it back to the head. And we clear the intermediate to failure, so back to 0 on the writer pointer to done. And then we return. Otherwise, we set the writer to success. That means so nobody else that was in that select group can trigger the writer. We unlock. And then we move our value from the writer to the reader. And then we set the close to false and add it to the executor. So then we can write a select range. There's one I wrote in select range, and there's one with variadics. We'll do the select range. We'll look at the select range because it's less hidden by metaprogramming stuff. So select range basically takes a range and then a function that we apply whenever we successfully read or write something in that range, when one of the channels gets triggers. So we have an awaiter, and then we return the awaiter. So this is what the awaiter looks like. So we store a pointer to the range, the function, a channel selector, and we store which node is selected, and a mutex. So as we did, we're never ready. Our suspend, so we take a lock at the beginning, and then we call read, passing in the selector on all the channel readers. And this is what read looks like. So we store the coroutine handle address. We set the node data to the awaiter, and then we set pdone, which was null pointer, we set it to the selector.done variable. And inside the wake up function, we actually lock and unlock the mutex, and that prevents a race condition where something can wake up before all the other parts of the selections have done the reads. And then we set the selected node and we wake up. That's the wake up function, the node.func, and then we pass it to read. Await resume, basically we go through the range, and what's interesting is, so we call remove for the node on every part, we call node.remove on the channel awaiter, so that removes it from any channel from the channel that it was in. And that's why we use a doubly linked list, because we can do remove in constant time. So then we check if the node that we are currently on is a selected node. Otherwise, if it is, we call the function, passing the value in, and we set the selected iterator to that. And finally, we return a pair with a Boolean that says whether it was closed or not, and the selected iterator. Sure. Why we need the unique lock. So right here, so in await suspend, so we're doing all these reads, right? So we don't want to be part of the reads, because once we start doing the iter remove, we want all the nodes that were in there to be cleared out of any channels. Because from then on, the coroutine may run and may destruct, and then we'd have dangling pointers. Does that make sense? Okay, so remove just, we'll call remove reader for its associated channel, which is just locks it and removes the head. Removes from the removes from the tail of the reader list. And at that point, basically, part of this, it's not there. Basically, sets all the previous and next pointers on the node to null pointer, so that way there's no error in calling this, even if it's already been removed. So this is again what our Go select writer looked like, and this is our channel select writer. So the only big difference is we have these channel wait writers, and pretty much the same code. If we are an even, we write to one, and odd, we write to the other. And the reader, so we do a select. Basically, we pass in what the channel reader is, and then a lambda. In this case, we're ignoring it, so we're not doing anything. And down at the bottom, p first, it will return whether the channel that was selected was closed or not. If it is, we break. And here's our code. So our code is about twice as slow as the callback code, and about 50, maybe 50% faster than the Go select. So then so some other features that we have. We add buffer channels. We won't go over that now. Allow select with read and writers to be mixed, and channel readers and writers for threads. This is basically more proof of concept stuff, so there's still a lot of stuff we can do in optimization. There's been no optimization other than removing the allocations. So going back to our thing, so channels can be a useful way to think about concurrency. This was our problem. So we read input serially, we process it, and we output it serially as well. Let's make it harder. Let's make the output in order. And let's recycle buffers. So basically what we're thinking of is maybe, hey, we have some sort of compression algorithm or something. You read in a block of a file. You send it off to a multi-threaded processor because it's CPU intensive. But then you want to write all the blocks that you read compressed, but you want to write them back in order. How do we go about doing this? I mean, I think it'd be difficult with futures, but we're going to try to do it with channels here. Anybody know what this is? Right. But we are going to use Sean Parent style, which is no synchronization primitives, right? No atomics, no mutexes, no barriers. So we're just going to use the channels. So here's how we do it. So let's just do some type aliases. We're going to have an array type that we're going to read 32 megs. Say we're going to read them in fixed block like that size. And we're going to make the payload unique pointer. And we're doing a unique pointer on purpose because it's move only. And then we do an order payload, which is an integer and a unique pointer. So this is what our reader looks like. So this is, I just did this on a simulation. So basically, we wouldn't have a count. We'd read from a file. So basically, increments an integer. And basically, first of all, it reads a payload type from a pool, reads from the pool channel. And then once it gets that, it maybe uses that to read from disk or something. And then we write that, moving it to the output channel. Any questions about this? So then the processor. So this is something, I guess, reading the Go does this a lot, where you can have like a make function that'll create like the channels that you need, like the output channel, run the whatever processor you have, and then return the output channel to you. So this creates the output channel for the channel to an ordered payload and runs the processor, spawns up a new processor, and returns the out channel. So this is what the processor looks like. We have an in channel and an out channel. And so we create the reader and writer. And then inside the channel itself, remember we're not doing anything other than setup, we make one of the array types. So we read from the reader. And then if the reader's closed, we close our out channel, and then we're done. And then we're just going to pretend to do some work. So we're going to sleep for a second. But in actuality, we might be using, so we've got two buffers now, the results.second.second and the out array. So we can maybe copy from one to the other, do some sort of compression. And then we write the out array, moving it to the output channel. And then we move the one that we read from the input channel, because we're done with it, because it's just the other stuff. We move it to be able to recycle it again for the next round. Now the writer is the one that's most complicated because we've got to reorder everything. So we actually have another channel to being able to signal when we're done. And then we have a channel to the pool because we want to return all these payload types back to the pool. So we create the writers, and then we create a vector of readers from the input channels. And then we create a vector of the ordered payload type for a reorder buffer. And then we reserve however many readers we have. And then we start with 0. And then the first thing we do is if we need to exit. So if the readers is empty, so there's no reader channels that we got, and there's nothing in the buffer, then we're done. So we just write true to done, and then we return. And then otherwise, we do a select range. So that's what we wrote. So we do a select on all the readers, and then we get the ordered payload out, right? So what we do is we then take it, push it into the reorder buffer, moving it, and then we use which is one of my favorite STL functions, push heap, so which will create like this one because of ordering, create a min heap. So that means that the smallest value is at reorder buffer.front. And then we also, so that takes care of the call to select range. And then we check if the channel that we actually selected we selected it because it was closed. So if it's closed, we just use that iterator that we got back in the second part to remove it from the readers. And then we have a loop while the reorder buffer is not empty, and we look to see if the first thing in the reorder buffer, that'll be sorted, that'll be a min heap for us, if the first is current. And then if that's the case, we know it's in order, we just do something to output it, we increment current, pop the heap, and then write that buffer back, write that payload back to the pool. So we recycle it back again for the reader to use. So once you've started everything and allocated it, there's no more memory allocations that happen. This is what we do for main. I have a little thing called channel runner that just was the channel executor, just creates a new thread and calls run on it. So we run however many threads we want. We create our input channel, the ordered payload type, the pool, and the done. And then we have so what we do is then we call the make processor and store them in the ordered payload channels for the processor. Remember the out channel that we got from the processor, so all the output channels from the processor we store in a vector, and we pass that vector to writer along with the done chan. And then this is not on here, but it's in the implementation. I wrote like a sync channel reader so you can use channels on a regular thread. So all you had to write is a reader and a writer, and you can use the channels will interoperate between fibers, between coroutines, and between regular threads. So in this case, we actually create a buffered channel. So if you look back here where the pool, it can take like a buffer size. So what it'll do is when you write, it'll non-block as long as you've got room in the buffer. So you create a bunch of the array types, we write them in there, and then we wait for it to complete. Any questions on this code? So basically, we don't have any synchronization primitives. Using channels, we've written something that can read from something, process in parallel, and write it back serially in order, and not allocate any memory while it's running. So basically, we've gone and we've taken at least Go channels and tried to bring them to the dark side of the force, right? So here's some more information. The concurrency TS. Here's some more. There's been some good talks on coroutines, and also there's a very nice article by Dmitry Vyukov about how how the underlying Go channels are implemented. If you want any code, that's here. All right, and I'll be happy to take any questions. And just remember, I use these channels for that. But like I said, if your compiler doesn't support it, but you have C++14, I've got some, you can either adapt this, or else I've got an implementation for, like I said, another implementation of library-based stackless coroutines. Thank you very much. Any questions? Yes.
So you're showing your GitHub code. Other than this presentation, do you have any articles or anything you've written on it?
I have not written any articles on this channel. Like I said, it was mainly for this presentation. It needs documentation, more articles and stuff like that for sure, and better packaging. Anything else? Yes, go ahead.
I barely know Go, but I think Go routines can talk to Go processes. Do you have any plans to do IPC kind of thing?
So the question is, the Go channels can do IPC, can do inter-process communication. I believe, at least unless they're implemented, you could, I believe it's intra-process as implemented, but what you can do is, to do intra-process communication, you could have another Go routine that sits between channels and that basically does the inter-process communication and then reads it from you, does the inter-process, and writes back the result to you. So you are communicating strictly with what you think is just a local channel, but the other Go routine can act as a proxy, and you're doing inter-process communication still using channels. Anything else? Yes, go ahead.
I'm not sure if I missed this, but can I reopen a channel once it's closed?
At this point, the question is, can a channel be reopened once it's closed? Currently, the answer is no, but I've been thinking about it, and I think it is possible to be able to do it. You just have to be careful how you do it, and there are some use cases where it could be useful. Go ahead. This was all, sorry, repeat the questions. So this was tested, this stuff was tested with Visual C++ 2015, like the highest optimizer levels for everything. It was on one program. And I've actually got this. So it actually used this one and let's see, channel select. These first two were actually I used with my the coroutine library just to test it out and comparing with futures and everything. And that was tested with GCC 6.203 on Ubuntu 16.04, and the results were roughly about the same relative to each other. Any other questions, comments? All right, then thank you very much for your attention.